So, good afternoon, everyone. I'm Stefan Kamga, Senior Architect here at Appian. I'm based in Milan and covering Southern Central Europe. So this is very much field experience. So for the next 45 minutes, we have one exciting topic and something most performance conversation gets wrong. So that's a tech talk, so no slide, just pattern that work at scale and from the real work. So because most performance problems are not discovered in production, they are designed in during sprint one. So let me start with a question. My goal today is not just to give you a pattern or a set of patterns, it's to help you build a mental model for scalability. So we'll use frequently analogies to things you can easily relate to demystify and simplify how Appian's work and how we should think about scalability. So since I'm based in Milan, I'll start with something you relate to. You know, Italian culture, restaurant, everyone knows about. So look at this place, and very packed, full, one team managing everything. So quick show of hand, who has already been in a similar place and everything was perfect, food arrived on time, no confusion, experience was good? Yeah, few people, good. Then the opposite one, who's been in a similar place and the experience was worse? Okay, we get many people. So basically nothing changed. It's the same picture, same restaurant, but completely different experience. And this is not related to the size or the number of customers in the restaurant. It's whether the kitchen was built and designed to handle that scale. So this is basically your Appian application. The users are coming. The question is whether did you design the kitchen to support that amount of user in mind? So before we talk about the patterns, we will talk about architecture. And we need to understand the fundamental question almost nobody asks. So today the agenda is pretty packed. So here's what we're going to do today. So notice the order is intentional. We'll start with where the time goes. Because if you can understand where the time fit in which bucket, you basically can, no pattern will be able to save you. Then we have 5 specific patterns addressing every category of a waste of time. Then we have a real use case from a banking customer and where we apply exactly this similar framework. And we'll close with the 5 rules you can take back to your team on Monday. So let's start with the most important question. The question nobody asks early in the development enough. And when I say time, I mean user perceived response time. So that's the thing that makes the user love your application or just hate it. This is the most important diagram of this first part of the session. I want you to look at it carefully. Everything inside the red box, UI rendering, rule evaluation, data access, synchronous process execution, is the user waiting, actively watching a spinner on the desktop. Everything in the green box, asynchronous work, the user has already moved on. So the work is still happening, but it's not visible to the end user. I call what is inside the red box the synchronous task. So every millisecond in that zone, it's a millisecond your user is actively paying. And the goal of everything we talk about today is how to shrink the red box and potentially increase the green one. That's not a technical choice, it's more an architectural mindset. So now let's get specific, because within the red box, the time is not distributed equally. So we start from UI rendering, which usually takes from 20 to 30%. Here's where times goes typically in most of the Appian requests. I've seen this across dozens of customer environments, and the distribution is surprisingly consistent. So the rule evaluation, that's where you have your business rule implemented, the decision table, you have all the different calculations. Then in the middle, you have the data access layer. Here you can have the record queries, the database write, and the data sync. And the last bucket, which is the asynchronous walk, is basically the process execution, the integration, and all the background job running. So if I ask you, when people usually think about scaling performance issue, which bucket is usually the first everyone think about? I've heard most of the time is, yeah, engine cannot scale and so on. But if you look at the numbers, the most important bucket is the data access one. Here is a simple example. Simple application. This table is the story I want you to remember in your next sprint planning. A simple form, 200 milliseconds for 10 users. You scale to 500 users, you still get the same time. That's linear, predictable, perfect. That's the best case. If you look at the different table, the difference between the row 2 and 3 is just one design decision, caching strategy. So that's it. The same functionality, the same business logic, but dramatically different scalability. So the performance problems don't appear at scale. They're basically always there. The scale will just make them visible. So that's the thing here. So to understand why this happened, let's look briefly at the architecture, the Appian architecture. You're all experts, so it's quick architecture review, not because you don't know this, but we need this as a shared map for the rest of the session. The user hit the web server, then goes to the application server, and from there, the request will simply fan out to different backend components. Might be database, Appian engine, file system, or search server. And when I talk about the 4 buckets before, each bucket map one or more of these different layers. So the UI rendering will live within web server, application server, and the data access will live maybe in the database hub or part in the asynchronous will live in the engine. So architecture is not just a diagram, it's a map where user time usually disappear when we think about these boxes. The good news is that each layer here can be tuned based on the use case. And this is really the good news, but it's also the trap. Because each layer can be scaled independently. Let's say you have database contention, you can tune the query or isolate that to a dedicated server for better resource usage. You have some process throughput limits. Yeah, you just say increase the engine chart, add CPU, and you're good to go. But there is the trap. Teams usually reach for architecture answer to design problem. And they add more engine when the real issue is probably not just the engine or could be something different. So infrastructure scaling should be the last resort. Design pattern first is the first line of defense. So architecture will buy you time, but good design will buy you scale. Let's go now one level deeper into the engine itself, which is one of the core of this session, because there is a specific misunderstanding about how that creates real design mistake. Welcome in the engine room. I see you're all excited. Good. So this is the engine room. Understanding what happened here change how you design. You have your process models. When you fire an instance, something will be created somewhere, and then the task will be completed. You have the engine, which is in-memory database, real-time, written in cakes, and the Java application server, which run on Java. So the K will evaluate the state transition of your process. It's working fast in memory with microsecond level. So this is not normally your bottleneck. The next node will need some work, and here we're talking about specific type of work. It could be sending an email, executing some expression, executing some smart service. So all these run on Java. So which means the application server will be responsible. So what will happen under the hood is that the K will create some work item. It will drop down into a queue. The Java work pooler will simply pick up that item, and it will forward to the specific handler. So whether it was an email or a plugin execution or whatever. And it's multi-threaded, that layer in Java, it's parallel, but it's bounded. So once the handler will complete, they will just mark back in K that the task is complete, and the process will resume. So it's a very complex room with in-memory speed engine working, and the Java, and the application server, which is running on Java. So here is what developer means. Every node you have in your process model, depending on how you will configure, could basically create this loop between the K and the Java layer. So a 20-node process will create 20 work items per instance. So at 1,000 concurrent user, that's 20,000 items in the queue. So the queue depth is also one of the real bottleneck, not the CPU, not the memory. So most people optimize just expression, but the real, where you can reduce how many loops you have, is happening where you reduce the interaction between the K and the Java. So every node round trip, you should design like every hop will cost you something. So here is just repeating exactly what we've just seen. So the loop happening within the engine room. And here we move to the other part of the mental model. So this is the last piece of the mental model. And then we'll move to the action. Everyone here have been in a supermarket, so you all know what I mean. Here is the analogy for the engine. So more lanes open, more customer per hour. That's throughput. That's what adding engine chart normally gives you. And by default, in Appian Cloud or whether self-managed, you have 3 checkout lanes. And by configuration changing, we can scale up to 32 checkout lanes. But it comes with some cost. You can't just shut down a checkout lanes when you don't need it anymore. So that's why we'll increase carefully. But again, a poorly designed process, even if you add 32 lanes, will not make that process faster. It will just create you 32 lines of poorly designed processes. So now we know where the time goes. Let's talk about it. The second part of what we're going through is 5 patterns that scale. So each will address specific bucket from the one we've just seen. We talk about record-centric design. We could talk about caching strategy. We talk about interface efficiency. And the last one will be the dynamic and horizontal scaling with autoscale. So these are not tips. They are simpler architectural commitment. And we start with the data access layer. The pattern 1, where we usually say stop querying and start relating. So records are simple data objects with built-in interface and contextual action. So how many process instances are you running at peak time, and which of those really need to be a process? Every process instance is a resource. The records don't have instances, so they just have some state representation of the data. So record-centric design reduces the process instance count entirely, and that's the deepest cut you can have for scalability. Fewer process running, less queue pressure, less K contention engine. And here, that's how it's looking in practice. This is a customer 360-degree view. And look at what's happening here. Related action embedded directly within the interface, contextual with one click, no navigation away, the task will launch and where the data exactly live. And the related records, orders, contact, service request, all surface through relationships, not repeated query going on. So you load the record once, and through the different relationships, everything associated is within one optimized call. This pattern will simply eliminate what I call the query sprawl. So, and that is one of the anti-pattern I want to show next. So we should just stop building up that fetch data, and we start building apps that simply relate the data. If you are not using record to build that customer 360-degree view, you're probably doing something similar. 4 queries on load, clean, readable, nothing obviously wrong, except that every user interaction reevaluates all 4 variables we see. And it could be user type or drop down, just 4 queries will be reevaluated and executed. If you have 10 interactions, that's basically going to be 40 database round trips. So the math here is silent until production. This afternoon, I think Jordan had a nice session where he talked about diagnosing bottlenecks in Appian, so which logs you need to see to identify all these type of bottlenecks. That is what we get when we adopt the record-centric approach. So instead of having 4 separate query entities call, we simply use the record data and with the relationship, and we'll be easily able to fetch the customer record once. And through the different relationships, we can get the order, the product, just everything coming along on the right in a single optimized call. So now look at the impact table from just moving and changing the approach. So the queries per load will go from 4 down to 1. The queries per evaluation will go from 4 down to 0. And after the 10 reevaluation, from 40 queries to 1. And that's almost 10 times reduction in the database calls. Same functionality, same data, but just a better data access pattern. But even with relationships, we're still going to have the data that will need to be fetched. And that's where caching comes in place. So we're going to the pattern number 2. And this is the one that separates, I've got it working in dev and I get it working at scale. So the fastest query is the one you never do. Remember. So if you can cache it, just do it. Now, it's a simple fix. We stop making query when we don't need, and we read from the cache when possible. So how to know when you should cache or not? We can just follow this simple decision tree. Does the data change frequently? If the answer is yes, we need to ask whether the user needs this real time. If the answer is yes, just don't cache. If the answer is no, so the short time to leave cache is fine. If the answer to the question, the data change frequently, is no, we should simply cache it aggressively if possible. And you'll be surprised if you run through this tree, how much of your data in your current application will be falling into this last category. Might be reference table, lookup value, config data. And so here, the table shows you 3 tools you have in mind to implement the different type of caching. The first one, the local variable. They're user specific, scope to the interface, simple to implement. The refresh variable, you control when it refresh. And the record, if you use record, is a different caching strategy, is basically handled at the platform level and it's shared across the user. So run this mentally every time you need to implement some data fetching in your solution. Here is another example, still related to caching. And it's probably the most expensive one line I've seen in Appian. A refresh interval of 1 means run this heavy query every second for every user actually navigating into this interface. So every second the user is watching the interface will run this query. So if we have 100 concurrent users, the page takes 200 milliseconds to execute. You've got 6,000 database round trip per minute just because of that one line. And I even gave a name to this one. It's a self-inflicted DDoS attack. And I've seen this bringing down production environment. The fix for this is pretty simple. You just configure the refresh on var change. This make only fire where the user explicitly trigger an action. Not every second, but on a more explicit control way. That's the principle. Now, let's move to pattern 3. Even if your queries are perfectly cached, there's still work that doesn't need to happen in front of the user. And that's all about pattern 3. The single biggest perceived performance win available in most of the Appian application. Don't make the user wait for an activity or a data that they don't need to see. We're all talking about mental models, so we'll have a bunch of trees, diagrams, just to relate easily. One question you should answer honestly during your design time is, must the user wait for a result? And if only if it's yes, keep it synchronously. Could be validation, quick calculation, interface updates, that's fine. But if the answer is no, and most backend work, the honest answer is no, just go asynchronously, start the process, queue the work, return the control to the end user. And it's easy to test. I usually apply one test is, does the user need to see this complete before they can do anything else? And this will usually tell you whether you need to go asynchronously or synchronously. Let me show you what we're actually talking about. So we have the top bar, which is the synchronous chain. Basically have 4 steps. 200 milliseconds, 800 milliseconds, 400 milliseconds, 600 milliseconds. It's 2 full seconds. It's pretty fast. That's what the user is watching. If we look the bottom bar, we have a different approach where we just fire and process. The user doesn't wait the handoff. So this one is 50 milliseconds. The rest happen in background and they're done. So it's the same business logic, the same outcome, but the same work getting done, but different timing. 2 seconds compared to 50 milliseconds. That is 40 times faster. Then we move to pattern 4, which is similar to the previous one, but it's good to mention it because we need to have that in mind during design time so we can build more scalable application. It's the other side of the question. What happens inside the interface when it will reevaluate? This one is pretty challenging, but once you get it, you will not miss it anymore. So if it doesn't need to change, just don't let it reevaluate. That's the tick. So every of these trigger a full interface reevaluation. Every single one. User typing in a field, clicking drop down change, clicking a button, a timer that will fire, and some variable dependency. All these will trigger interface to reevaluate. The fix here is simple, just one line. Refresh on var change. This will simply load once and refresh only when the search will be clicked in this example. Because sale reevaluate by default, so our job is pretty to control and be selective on the reevaluation. The last pattern is about what happens when none of these design implementation are enough, because the volume itself is just unpredictable and enormous. The Appian answer to this question, what's happened when good design has been applied is not enough because the volume are simply massive. Here we are back again in the engine room, our favorite room. And understanding what happened inside will change how we approach some design decision. So we have seen how process run. There might be trigger, interface from API, from portal, and it will just spin up a new process instance that will run in one engine, execution engine. And just to come back to the original mental model and analogy, this is going to sit in a dedicated checkout lanes. So each one is consuming engine resource, and they are fixed provision, always on. So you provision for the peak, and you pay for it even when the demand is low. And remember, from the mental model, you can't close the checkout lane once you're provisioned. And we did that model, which I will call the standard engine execution mode. We have 2 modes of execution. The foreground is user-attended, fast individual execution, lower throughput. This is also linked to our original mental model. Foreground is your express lane for the checkout. It's fast, attended, but you have some limited item in the cart, just 50. The background will be for the high throughput, process step together in batches. It's probably slower, but help you to achieve much more volume, and it gets good fit for different use case. So both still bound by the provision resource on your environment. Now, here is where it's getting interesting. The standard mode, synchronous, 50 node max. The background mode, can scale to 2 million processes per working day. If we look at the real enterprise demand, it's rarely flat. So customers face different realities. You get predictable peaks, month-end closure, specific jobs, yearly closure cycles, and you have unpredictable ones. Backlog dump, migration, marketing campaign, or whatever. So the fixed provisioning cannot answer the both needs. That's exactly where AutoScale sits. So it's isolated from your Appian engine, outside your environment limits, so provision dynamically based on the actual real demand, and it can scale up to 6 million processes per hour. So moving from statistically provisioned engine to dynamic provisioning based on the demand, that's what you get when we go with AutoScale. So no infrastructure change, no redeployment. AutoScale will simply offload the execution entirely from your main node, and it will execute the process end-to-end and free your environment resources for everything else. When the work just builds up in the queue, the executor, which are the different type of lanes, the checkout lanes, the special one, they will just automatically be spin up to handle the expected spike and all the heavy seasonal work. And the best part is enabling AutoScale is just one flag in your process model. You just tick, run AutoScale. And that's what will help you achieve unlimited capacity. Then we need to look a little bit at a case study. Here is the starting point. It's a real banking application. If you want to look at the balance scale at the moment, on the cost side, we have a few things, to be honest. So excessive queries, long-running processes, synchronous call going around, too many K to Java loops, probably sometimes unnecessary loops, and too many nodes in different processes, no data fabric use, which was very shocking, and the scale is tip hard left. On the pro side, we also had some correct pattern applied. So the activity chaining was applied pretty good. So where specifically needed. Some batch strategy was implemented, but the team wasn't incompetent. That's what the take here. They were just working without a scalability framework. And you see from the screenshot, for example, the 90 queries configured on the script task, some of the things not storing in any process variable. So, and this was from production environment. So many different unnecessary queries and complex operation that will just simply increase the K to Java loops we just review in the mental model. So here are some numbers. Few items in the work pool or queue, and that's not a spike, it's a structural bottleneck. So the work peeling up faster than it can execute, basically. 90 queries for a single customer 360-degree load. That's what you pay when you don't use Record, as we've seen. So too many queries just to build up some 360-degree customer view. And so which means one user opening a customer page will fire 90 database query round trips between to see anything. And some store procedure, slow store procedure, not optimized running, and several times. So this even worked for fewer users and fewer records, but it couldn't scale to meet the real business demand. So this is the power of having the mental model. Once you can name every bucket where you are challenges or you don't have good enough response time, it's more easy and obvious to find some solution. So talking about the queries, for example, we simply introduce the record usage and relationship plus the data fabric. This helped to reduce minus 16 query just to rebuild the same experience. The 60 hits on the income rule was just replaced by some nested, so the nested loop flatten were just replaced here with record relationship join. The result here was 92% database hit reduction, and the sequential writes unusable sometime were just consolidated into fewer transactions, and this produced fewer writes. The synchronous SOAP call that was happening was actually not very necessary for the end user to wait, so we apply one of the pattern we review, and that's basically helped to reduce globally the different timing. So here are some key results we obtained. I'm not just going to list them everywhere. Everything here was applied in very few amount of time. So when you know what you want to fix, basically applying the fix could be very fast. So we need the mental model to guide our resolution path. Now, I will go with the last 5 rules I want you to take back to your team for next week. The first rule is you need to design for 10 times your current load. This will save you a lot of time. So if you design for today's 100 user, you'll fail at tomorrow 200 user. That's the thing. The second rule is that synchronous is expensive. So every synchronous call is a user actually watching the spinner. So we need to remember the synchronous tax. The rule number 3 is we need to apply caching, and we need to apply caching strategically. So the fastest query is the one we never make. That's the thing we need to remember. The rule number 4, and really in line with the session before David gave you, is that we need to measure before we optimize. So intuition will lie. Metrics will never lie. Apply performance testing. And the last but not the least, which sometimes we can understand is not always achievable for maybe for the infrastructure, but it's what we should be doing, is we need to test with production-like data and production-like environments. So I think that was all. We're pretty in time. We could catch up on the time, and thank you for listening. Any question? I think so, maybe.
I was just asking, where can we access these slides later on?
I'm asking, I can't get an answer.
Okay.
Usually they're shared after the conference, so that's the usual pattern.
Yeah, I love this presentation, actually. But even though, do you have some educational class or thing about this?
Oh, no, but it's
online
something we're
software?
probably working on.
Because I want to give them all my this one to all my developers. They have to pass this test before they start to develop.
Do you have any recommendations on the best approach to manage the Appian native task system? Because we found that we were almost like fork bombing ourselves with certain volumes of tasks. And so we ended up doing what a lot of customers do, which is building our own, let's say, more database-driven approach with a custom record and whatnot. But we found that we lost a lot of native functionality, including like alerts and whatnot. And we tried to replicate it, but it's not as good. So do you have any thoughts on that?
Yeah, I think there is no one size fits all. So the standard native task is you get it for free. You don't have to implement anything. I do agree in some specific cases, you will probably have to implement your own database-driven tasks, or what you mentioned, but that's a design decision. So there is no go-to recommendation. Depending on the use case, you'd rather agree implementing a task, and in that case, yeah, you probably need to implement partially what's already out of the box with the out-of-the-box taxi.
Can you just elaborate on some more of those, like the Java work items you were talking about? Like, what are just some other examples of those?
Okay, you mean in the engine room, correct?
Right.
Yeah, I think that was very passionate for everyone. So if we back in the engine room, I think the finding here is pretty interesting, because when you understand how this work internally, you will realize that the fewer task or script tasks you put in the process, the fewer potential loop you will have, because as I explained, the engine is in-memory database implemented in a different language or technology, which is cakes. The application server will be running on Java, so they don't talk the same language. And they both rely on each other. So when the engine will have something where it needs a specific handler, let's say sending an email, he will rely on Java for that. So there is this internal mechanism to pass the work from the engine to the Java layer, and that will just sit in the queue. And when that work is complete, it will just be shipped back to the engine to say, "Mark done, I'm finished." So everything that is running in Java will be smart service, expression, email, or whatever other I miss here, will always rely there. And for the engine, it's more about the transitional state dynamic happening in memory fast, which will remain in the engine.
So save it in a variable or a record relationship and just reuse
Yeah,
that.
correct. Reducing the number of, script tasks, even within the script task, the different activity class parameter we will have with complex logic, that will all then save the round trip from the K to Java I just explained. Any other question?
Real quick, I have the answer about the slides.
Okay.
Slides will not be posted, but the session is being recorded and will be on the Appian community YouTube channel. So you can check it out there, and then we're also going to be updating some online courses and other content. So you can definitely find the session on YouTube.
All right, thanks. Well, thank you.